Okay, so we are recording now.
There is also a live stream component, I guess.
Yeah, actually, I'll try it one of these days. So today I'm not live streaming it. I'll do it like last time. Record and upload it shortly.
Okay.
But eventually, I think I'll go to live stream because that's, I mean, save some time, computing time on my computer. Like then Zoom has to convert it, then YouTube has to convert it, check it. YouTube does a lot of checks.
Yeah.
This whole process takes about half an hour. Yeah. Okay. Yeah. So previously we recapitulated Shannon's noiseless source coding theorem, the asymptotic IID version. So we saw the traditional proof, and then we proved our one-shot noiseless source coding theorem. And if you look at the slides that I posted, I updated them slightly. So in fact, in the one-shot case, you can give the exact answer. It is ceiling of H max epsilon s. Okay, so I said it's between H max epsilon plus or H max epsilon plus 1, but really, I mean, more honestly speaking, it is exactly the ceiling. Okay, so you can look at the updated slides where this correction has been made. Okay, and some more reasoning has been given to explain why this is the case. So recall we defined this new smooth entropic quantity. Okay, so this was the H epsilon max. So what is that? Let's recall, as Ishan, rightly guessed. So take a probability distribution PS, arrange the elements of the sample space in descending order of their probabilities like this, and then look at the smallest elements whose probabilities sum up to at most epsilon. So that is this tail out here, and I'm going to zero it out basically. So look at the remaining guys which are not zeroed out. So that's what I call the smoothed support S prime. So support just means the points where the probability is non-zero. So this is smoothed support. So this operation of throwing away some tail or some head, I mean, perturbing the original distribution is called smoothing. Okay, and the smoothed entropies are crucially used in one-shot theory. Okay. So our definition of H max epsilon is the log of the size of the smoothed support. And as we saw, the one-shot theorem, okay, already beats the IID theorem, both in the achievability and in the converse. Okay, so any questions from the last time?
Can you briefly recall that shifting argument? In the shifting argument, why at one point is sort of left out?
Shifting argument, sure. Okay, before going there, we have a new participant, so maybe I'd like to hear from you, Sahil. You are there, right?
Yeah, hi.
Yeah, hi. So what's your background in linear algebra or information theory?
Yeah, I've done a course. I've done linear algebra, and I've self-studied information theory from David McKay's textbook. And
okay, so you have seen Shannon's noisy channel coding theory.
Yeah, I have.
Okay, good. Okay. Have you done the tensor product?
Yeah, I've done.
Okay. Okay, I think then you are
graduate algebra.
Yeah. Okay. So then you're pretty well prepared for the course. So the linear algebra will kick in the second half when we do the quantum information theory. Okay, so the shifting arguments. So let me go back. Actually, it's there in the other. Let me share the other thing. It's there.
I think you have drawn something.
Yeah. So the drawn slides are the ones that are uploaded. Let me pull it out from the Slack channel, and I will display that. So let me share something else. You can see this now, right?
Yeah.
Yeah. So this has the shifting argument. So Ishan, is the LP formulation clear?
Yes.
Yeah. So so recall we have mathematically modeled the process of encoding the sample S, which is outputted by the probabilistic source, encoding and then decoding. So, and the overall success probability of decoding is captured by this expression, and this we want to be larger than 1 minus epsilon. Okay, and then the quantity in brackets, we gave it the name lambda S, and lambda S is nothing but the probability of decoding S correctly. So given that the symbol S has been outputted, it goes to a randomized encoder, and then it goes to a randomized decoder. So what's the probability that this particular S is decoded correctly? That's lambda S. So it's a quantity between 0 and 1. And then there was this one-line argument which says that the size of the code space is lower bounded by summation lambda S. Okay. So if I want to minimize E, then it makes sense to minimize summation lambda S, and that led us to this LP. Okay, that I want to minimize summation lambda S subject to these constraints. Okay, so here is the shifting argument again. So arrange the elements of the sample space in descending order of the probabilities. Okay, so arrange S in descending order of PS. So the diagram looks like this. Now, for every S, there is a lambda S. Okay, so let us look at the optimal solution to this. There is some lambda S, and all I know is that for any S, lambda S is between 0 and 1. Nothing more I know. Now, the idea is to shift lambda S to the left, ensuring that the objective function, namely the summation of lambda S, stays the same. And the vector of lambda continues to be feasible. Continues to be feasible means it satisfies these constraints. In particular, the success probability is larger than 1 minus epsilon. So this is what I have to do. So what was the argument? Start from the rightmost guy. So this is the S with the smallest PS. So it has some lambda S, let us say greater than 0. I will try to decrease it by a very small amount theta. So I'll go from lambda S to lambda S minus theta. And I want to keep the summation lambda as the same. So I'll shift theta to a lambda S somewhere out here on the left. Okay. So if I can shift the entire, shift the mass theta from the rightmost guy to something out here, then of course summation lambda stays the same. And in fact, the success probability can only go up, because decreasing the last lambdas by theta, of course, decreases the contribution to the success probability here for the last S, but then it is more than compensated by the extra theta somewhere here. So remember, the probability of this guy is larger than the probability of the last guy. So no matter where I shift theta, the place where theta lands up in, somewhere here, so this guy will have probability larger than the very last guy. Okay, so it continues to be feasible. And the idea is I keep doing this. So I keep shifting theta, theta, theta out from the rightmost guy till the rightmost guy has lambda is equal to 0. Then I go to the next to the last guy and keep doing this. So when will this process stop? This process will stop. So it stops, let's say, somewhere here. So here there is a lambda S, let us say between 0 and 1, but I can't even shift any non-zero theta. The reason is, remember, I'm shifting to the left. So the reason I cannot even shift a minuscule theta is because all these lambda S's are 1. That's when this process stops. Is that clear, Ishan?
Yes. Just the meaning. So when we say shift lambda S, so lambda S is the probability of correctly decoding S.
Yes.
But
yes, right now I'm talking to the LP.
Okay. But just kind of to just to understand it, like what does it mean when we say that I'm shifting the say lambda?
So what I'm doing is I'm thinking of a new decoding scheme where the decoder decodes the rightmost S with a little lesser probability. So that it is lambda S minus theta, and it decodes some S to the S prime to the left with a slightly better probability, lambda S prime plus theta. Okay. So this shifting operation means I'm changing my decoding strategy. Remember, I want to show that no decoding strategy, no combination of encoding and decoding strategies can do better than H max epsilon. Okay. So I have I've said that if there's a decoding strategy, there's an LP, and then I'm just analyzing that LP, and I'm saying that no LP can do better than some blah blah. So that's how the proof goes. Okay, so this is a converse. So this is not an achievability proof. This is a converse.
Oh, okay.
But nevertheless, there is an operational meaning, which means that I'm changing the decoding strategy. So I'll decode the smallest s with a little lesser probability, and I'll decode some s prime, some other s prime with a little higher probability. Okay, that's what it means. Okay, any questions about this? Okay, so yeah, so let's just finish for the record. So this process stopped because all these lambda s's are 1. So this is maybe something between 0 and 1, and and to the right, all these lambda s's have been zeroed out, and this is still a feasible solution. Okay, and now because this is a feasible solution, what do I have? I can conclude that the probabilities of the tail out here. So what is the tail? The tail is where lambda s is equal to 0. So their probabilities, their PS terms, when added up, will give me less than epsilon. So why is that? If I look at the success probability is entirely determined by these guys. So the left guys plus this one guy, and because the new lambda vector is still feasible, the success probability is larger than 1 minus epsilon. So I am in fact going above the success probability by even adding the PS for this threshold guy. Let's call this threshold guy S0. So this quantity would look like summation PS, where S is to the left of S0 plus lambda S0 PS0. But now I'm saying that upper bound lambda S0 also by 1, and now look at summation S, where S ranges to the left guys plus summation PS0. So this will be even larger, and this will continue to be larger than 1 minus epsilon, which means the remaining guys have to be less than epsilon. So this is a candidate for my H max epsilon, and that finishes the rest of the argument. So my code space, remember, my code space, I have to encode, of course, all the non-zero lambdas, guys. So that's my code space E, and then log E becomes H max epsilon. Okay. So note that this argument also shows that if I go one level higher up, like if I add this S0 to my tail, then I will overshoot epsilon. Okay, is it clear? Okay, any further questions? If not, let's go back to today's topic. Yeah. So, okay. So today, are the slides visible to everybody? Okay. So today, we will recapitulate Shannon's noisy channel coding theorem, the asymptotic IID version. We'll see what was Shannon's original proof, like very quick and high level. And then we'll do some technical stuff. We will study a quantity called the relative entropy, which is the mother quantity behind all the other entropy quantities that you may have studied or heard of. So what is the noisy channel coding theorem, first of all? So I have a channel C, so that is mathematically modeled by mapping the input symbol X to a probability distribution on the output symbols Y. Okay, so I denoted by this conditional probability distribution P of Y given X. So for a fixed input symbol X, the output of the channel is a probability distribution on Y given by this. Okay. So the reason it's called noisy is because the output is a probability distribution. So that captures the noise. So think of it as the channel transmits X but introduces some noise. So this probability distribution might be peaked on X, but there will be peaked on Y equal to X, but there will be some non-zero probabilities on other Y primes. Okay, so here is the channel. characteristics of the channel, namely these conditional probability distributions for every x are known to us. Now fix two parameters, epsilon and delta, between 0 and 1. Now the sender Alice wants to send a message. So the message is a number from 1 to 2 to the nr, okay? And we'll call r as the rate and per channel use, which will become clear very soon. Now, we are going to analyze the error probability of this entire process when the message to be transmitted is chosen uniformly at random from this set. And let us say this quantity R, this so-called rate per channel use, is less than this number. So what is this number? So there is this new quantity which is called the mutual information between X and Y. So recall what is X. So I have the channel. X is the input alphabet to the channel, and Y is the output alphabet. And note that the channel maps a symbol X to a probability distribution over little y's, over symbols in the output alphabet. Now suppose I put in a probability distribution at the input, so that is this Px. Okay. Then I can think of the joint probability distribution on X and Y, right? So the marginal on the input is Px, but then there will be joint distribution mediated by this conditional out here. So this subscript P reminds you of the joint probability distribution on X and Y. So under this joint probability distribution, I can define this entropy quantity called mutual information. So this is the formula: entropy of X plus entropy of Y minus entropy of X. So here is the entropy of X, just thinking of the marginal distribution X. This is the entropy of the output, just think of the marginal distribution on the output. Okay, so where I've averaged over all little x. And this is the entropy of the joint probability distribution on X, Y. So remember, when the asymptotic IID setting, the channel is used independently many times. Okay, and we are looking at the maximum rate per channel use, which is called the channel capacity. And here is my suggestion for the channel capacity. So look at this quantity. Of course, this quantity depends upon what is the input distribution that I'm supplying to X. So maximize the mutual information over all input distributions. So that is the right-hand side. And I claim that basically that is this capacity. Why? So for large enough n, so large enough n means this threshold depends on the characteristics of the channel. So basically on this conditional probability distribution, it depends on epsilon delta. But for large enough n, there is a deterministic encoder E, which maps the message M to a code word. So the code word I'm going to call xn. So the code word is an n tuple of symbols X from the input alphabet of C. So the input alphabet of C is just one copy of X, but I'm not mapping M to one copy of one symbol X. I'm mapping M to an n tuple. Okay, so this is a notation for the n tuple, if you recall. So xm is an n tuple of symbols from the alphabet capital X. Okay, so that's the code word. Now that passes through the channel, so there are n independent copies of the channel. So I get some distribution output. So the distribution is over n tuples of y, okay, n tuples of little y. So I get some distribution. Now the decoder gets a sample from this distribution, these n tuples, and tries his best to decode, and he outputs some m hat. M hat is the guess for m. And what we want is the probability that m hat is not equal to m is less than or equal to epsilon. Okay. So remember, the probability is calculated over the random choice of m and the randomness of C. So right now I'm thinking of deterministic encoding, deterministic decoding. So the source of randomness is the choice of m and the randomness introduced by the channel. And the achievability result of Shannon says that as long as the rate per channel use, okay? So you can see why it's called the rate per channel. So this is the number of messages that I can send. Okay, so the total number of messages is 2 to the nr. Log of that, when I'm measuring in bits, is nr. Per channel use, the bit rate is r. So if the rate is less than this capacity, then for large enough n, I can indeed get transmission with very small error, less than epsilon error. Okay, and there is also a converse to Shannon. So the converse says that any private coin, so the converse is slightly stronger, any private coin randomized encoding and decoding strategy. Okay, so the achievability works even with deterministic encoding and decoding, but the converse holds true for randomized encoding also. So the encoder can use his own private coins, decoder can use his own private coins for decoding. So any randomized strategy that succeeds with probability at least epsilon. Okay. So remember the success probability for the achievability was 1 minus epsilon. But the converse is stronger even in that sense. It says that even if the success probability is epsilon, then the rate has to be basically less than the capacity. So, but you can see the fudge factor of 1 minus delta and 1 plus delta. Okay. So there's a little bit of gap between them. But nevertheless, so what is the capacity? The capacity is defined to be the maximum of the mutual information. Okay, so ignoring this fudge factor. So people loosely say that any rate below the capacity can be achieved with probability of error very very small. So that formally this is the rate can be achieved. Remember, delta can be taken as small as possible. The price that you pay is in this threshold here. And people say there's the converse that that if I want non-trivial success probability of decoding, then the rate has to be less than the capacity. So yeah, so both form there is this fudge factor, but that's what it means. And again, remember delta can be made as small as we want. Any questions about the statement on this theorem? No? Okay. So let's go ahead. So let's recall the proof in the traditional classes. Okay, so the proof goes by a technique which is called the random codebook construction. So it is nothing but an application of the probabilistic method. You may have seen the probabilistic method in combinatorics, graph theory kind of thing. So this is the same method philosophically. So this was independently rediscovered by Shannon in the context of information. So here is what we do. So I want to construct the code book. So for every message n, I want to tell what is the code word xn. So how do we construct the code word? So the code book is a set of code words for every possible message. So how do I construct the code book? So for the first message, just choose a random string, a random n tuple xn. So this n tuple is chosen according to this probability distribution. Note that this just means n IID copies of the base probability distribution on x, and the base probability distribution is this px that I'm talking. So fix a px out here. So fix a px which is close to the maximum or achieves the maximum. Fine. Now that px is the base probability distribution in single copy x. Now take n IID copies of px. Okay, so that's the probability distribution on x to the tensor power n. Now choose a symbol xn. Okay, and that's it. And say that this is my code word for the first message. Then for the second message, repeat the same process independently. Okay, so I get some string, maybe same, maybe different. Call that my code word for the second message, and keep doing it for all the messages. Okay? So this is done independently according to the probability distribution on x to the tensor power. So once I get the random codebook C, it is revealed to both the encoder and the decoder. And henceforth the encoder and the decoder are deterministic. Okay, so this random codebook is only for the construction. Okay, once the codebook has been chosen, it's revealed to the encoder and decoder, and they will behave deterministically. The encoder is very simple. To send a particular message, the encoder just takes the code word corresponding to that, which is some xn in brackets n, and feeds it to n independent copies of the channel. Okay, as you can see. Okay, that's it. And now the channel produces some output. So the output is a probability distribution over n tuples of y. Okay, so let us say let y to the power n be the random string at the output of n copies of the channel. Now the decoder D follows a deterministic sequential decoding strategy. Okay, so people who have seen this argument, you may have, you would have seen maybe a quicker argument which says that okay, do some joint typicality and unique message which is jointly typical, so on. So it's basically the same thing, but we are just fleshing it out. we are making it more algorithmic, which will help for our purposes. So the sequential decoding strategy is as follows. The decoder cycles through all candidate messages m hat from 1 to 2 to the error. And for each candidate message, he looks at the code word for that candidate message, which is this xn m hat, and he checks whether the tuple xn m hat and yn is the output of the channel. He checks if this tuple is jointly typical. So this is jointly typical means according to the joint probability distribution on xy. Remember, like I defined this probability distribution on xy out here. So according to the joint probability distribution, this should be typical. Okay, we defined typical in the last class. We are going to look at it again. I'm thinking of frequency typical out here. Okay, so if this is jointly typical, then output the current guess m hat and stop, or else go to the next candidate m hat. And what happens if you exhaust all the m hats and still don't see anything jointly typical? You just output an error, or let us say I output m hat equal to 1. Doesn't matter. So this will go into the error analysis. So more precisely, saying that this tuple is jointly typical means the following. So this is, remember, this is an n tuple. So I'm writing the n tuple like this. So the first coordinate is the code word for m hat. Look at the first coordinate of that. Basically, what was fed to the first channel. So that together with y1. Y1 was the output of the first channel. So similarly, for the second channel, look at what was fed to the second channel, the symbol and the output here. So this is the n tuple. So this is the n tuple of pairs. So saying that this is jointly typical means that this string is delta frequency typical with respect to the random variable xy. And this is the joint probability distribution, which I like to denote as the input probability distribution px times the conditional brought in by the channel. Is this clear?
I think there, like, it's so. Just can you just go to the previous slide?
Yeah.
So this, so there is some notational fudging here, right? I mean, this should be p sub x. I mean, what do you mean when you say this x to the tensor power n is the product of n px's?
I did say that it is n independent copies of px. So px is the base probability distribution on a single copy x, and this is the n copies of it. And the same thing is also implied here. Like, so on one copy of the random variable xy, okay, on the joint random variable xy, on one copy the base probability distribution is given by this, okay. And now I take n copies of xy. So I'm saying that this string is delta frequency typical with respect to that. Okay. So that's what it is. So there's really no new concept out here. It's just that the random variable has now become a joint random variable xy, but it's still a random variable. And then all of it makes sense. Any further questions? It will become clear in the next slide when we, start doing the error analysis. We will see what is jointly typical with what. Okay. So let us try to analyze the decoding error. So the way we'll do it is we'll analyze the expectation of the decoding error probability. So the expectation is taken over the choice of the random code books. So let's fix the notation. Let yn be the random string at the output of n copies of the channel when m is transmitted. So let's say I'm thinking of a fixed m. So this m is fixed. It goes to a deterministic decoding because if the code book is fixed. And then the channel introduces some noise. So the output is a random variable. Let yn be a sample from that random variable. And then it goes to deterministic decoder. And out comes m hat. So I can think of the probability that m hat is not equal to m, given that m is transmitted. So this is the notation. So of course, this probability depends upon the choice of the code book. So I can take the expectation of it over the choice of the random code. So now this is the quantity on the left-hand side, which I'm going to analyze. Okay. So this is what is called the expected decoding error problem. So as we saw in the algorithm, when does an error occur? Error occurs if yn is not jointly typical with the actual transmitted message. Okay. So remember, the decoding algorithm was cycling through all candidates n hat, going from 1 to 2 to the nr. So for m hat equal to m, suppose by bad luck the output yn is not jointly typical with the true code word. So then of course there will be an error. Or yn is jointly typical with some earlier code word. So m hat is less than n. Okay. By bad luck, yn is jointly typical with respect to some earlier code word. So even if this happens, this is an error. Okay. So the overall error event is equal to the this event. Okay. So this is the union of several events out here, as you can see. So this is in union with this, and then there's an implicit union over all m hat out here. So that's the probability. Then I continue to take the expectation. Then I'll use the union bound on probabilities. Okay. So this is less than the probability that yn is not jointly typical with the true code word. Okay. Plus, continue to take union bound. Yn is jointly typical with the m prime code word, where m prime is earlier than m. And you can see the summation here over all the earlier m primes. Okay. Any questions about this? Okay, let's go ahead. Okay, so we were here. So we had this union bound out here. And now I'm going to further upper bound it. So let us look at the first guy. So what is the probability that yn is not jointly typical with the transmitted code word? And I'm taking the expectation of this probability over the choice of the random code book. So note that when I'm taking the expectation over the random code book, then this code word, the mth code word, is nothing but a string chosen from the probability distribution on x to the power n. And remember, this probability distribution x to the power n is n independent copies of the base probability distribution px. So I can now ignore this entire m. So I can just look at this question in probability theory. So I have a probability distribution on strings xn, okay, pxn. Then of course the channel acts on xn and produces yn, but that actually is captured by this probability of yn given xn. And again, this conditional probability distribution breaks up into a product of probability distributions, okay, because the channel acts independently. Okay. So the probability distributions are not identical simply because the first coordinate of xn in general is different from the second coordinate of xn and so forth. So the conditional distributions that the channel sees are different, but nevertheless is independent. So it's independent but differently distributed. That's what this conditional probability distribution looks like. But what is this? This is the joint probability distribution on the string xn, comma yn. And now I'm asking, what is the probability that xn is not jointly typical with yn under this joint probability distribution? Okay. So that is precisely the value of the first term out here captured. Now for the second term, so this is where the inequality becomes strict, because this was ranging from 1 to m-1, whereas I'm throwing up my hands and saying that whatever it is less than 2 to the nr. So 2 to the nr, and now what is this? So this expression is the expectation of yn being jointly typical with some m prime, different from the transmitted m. Okay. So this is the same for all m primes. So that's why I'm dropping all m primes out. So why is that the case? So what is the probability distribution on xn m prime? Remember, the code book is chosen randomly. So this probability distribution is nothing but choosing a random sample from x to the power. So that is px to the n. Okay. Now remember, yn is the output of the channel. So yn is expected to be jointly typical with x and m. It is independent of x and m prime. Okay. So the probability distribution on yn is nothing but the marginal probability distribution Pyn. And now the question is, what is the chance that yn is jointly typical with xn under this kind of probability distribution? Okay. And you expect that this will be very small. So is this argument clear?
No, 1 second. So this event. So yn is jointly typical with xn. The event inside is that yn is jointly typical with xn with respect to the joint distribution, but the probability is being taken with respect to the product distribution. That is the correct.
Yes. So you are right. Yeah. So the definition of joint typicality is with respect to this delta frequency typical with respect to the joint distribution. Okay. So that is the definition of this. So that's an event. So I'm analyzing the probability of this event under this distribution.
Essentially what is being said is, so the first thing is that, okay, I don't know what m is, so I'll just upper bound it. I'll take the worst case and I'll analyze this event thinking of this m as the last message in the lexicographic order.
Kind of, yeah. I mean, yeah.
That's why we're taking the 2 to the n. And the second thing, what this probability expression is saying is that given a sample from a jointly given sample from the product distribution, what is the probability that it is also jointly typical with respect to the joint distribution? That is the thing.
Yes. Yeah. So again, the last quantity is given a sample from the product distribution. Here, what is the probability is jointly typical with respect to the joint distribution? Okay. So the word jointly typical is supposed to remind you that it's defined with respect to the joint distribution. Okay. So remember, joint typicality is an event. Event means it's a subset of strings. Okay. Now to define that event, I have to think of the joint distribution, but I mean, after I am done with that, it's just a subset of strings. Okay, so it's an event, and I can think of the probability of this subset of strings under whatever probability distribution I want. I can look at the probability of this subset of strings under this distribution or under this distribution. Okay? So under this distribution, I expect it to be high. Okay, and under this distribution, I expect it to be low. That's all. Okay, is it clear to everybody? Okay. So let's go ahead. So we have upper bounded the expected decoding error probability by this quantity. Okay. So now all the m primes have gone away. Okay. And the claim is this is upper bounded further by something which looks like epsilon plus 2 to the nr times a certain entropy quantity. So why is that? So recall in the last lecture, probability of x and yn being delta frequency typical under the joint distribution. Okay, so this was what I meant by jointly typical. So that is at least 1 minus epsilon. So this we saw when we were doing Shannon's noiseless coding theorem, that after we defined what it means to be delta frequency typical. So if you take a sample from a probability distribution, n copies of the probability distribution, then the probability of lying in a typical set is at least 1 minus epsilon. So it doesn't matter that the distribution is not over x to the n, but over xn comma y. Is the same theorem out here. So this is the easy part. So this gives epsilon out here. So the harder part is this, which we didn't see last time. Okay, we will not see a proof of it, at least not directly in this course, but this is very standard. So you can look at any standard text in information theory like Cover and Thomas or El-Gamal Kim to see a proof of this. So the probability of xn comma yn being typical under the product distribution. So remember, being typical is an event, it's a subset. So the probability of this subset under the product distribution is very small. So in particular, it is bounded between these two quantities. So this plus minus delta means that the probability is upper bounded by one of these quantities. I mean, the probability is upper bounded when I have a minus out here, and the probability is lower bounded when I have a plus out Okay. So the probability of a sample from the product distribution being jointly typical with respect to the joint distribution, being typical with respect to joint distribution, is tightly bounded between these two extremes. Okay. Anyway, we only want the upper bound, so we are going to put it out here, and that's what we put. Any questions? Yeah. So maybe it pays to draw a diagram out here to see what we say. So let us say so. This is how things look like, and so this is x. Okay. So these are points little x coming from the set X, and these are okay. This side is Y. Okay. So for a given little x, I get a probability distribution on Y. Okay. Let us say it looks like a blob. I mean, there might be little mass outside the blob, but let's say in some intuitive sense, most of the mass is in this blob. So similarly, this is another xn, and there's a blob corresponding. There's another xn, there's a blob corresponding. The point is, when you go to n independent copies, you start getting this concentration. Okay. Your base probability distribution could have been anything, but once you go to n independent copies, most of the mass lies in a blob. Okay. And you can actually bound what is the size of this blob in terms of entropy quantities. Okay. And then you can ask, for example, so okay, so when I'm talking the jointly typical set, it is basically the union of these cones. Okay, so there's the blobs here, and then is the union of this cone. So I'll take the union over the typical x's. So so I have a blob for every little x, but let us say these are the typical x's. Okay, so the jointly typical set is the union of these blobs where the vertex points of the cones come from the typical axis. And now, whereas the product probability distribution will be something else. So it will be the product set of two blobs. One blob on the left hand side for the typical guys. Okay. So for X it is this, and for Y there will be some typical set out here. So let me draw a different kind of thing out here. So let us say for the product distribution, again things are concentrated in the typical set for X times the typical set for Y, and it sort of looks like this. And now, and once I mean you have this picture in mind, then you can calculate what fraction of these cones intersects with this part, and you will end up with a quantity something like this.
I mean, here's a sort of a slightly simpler reason, right? That if you look at this product distribution, the n copy product distribution of Pxn and Pyn, how many guys are inside? There are roughly 2 to the nhx plus hy guys in the
Correct.
right. Yeah. And how many guys are in the typical set of the joint distribution is 2 to the nhx x comma y. But then I'm going to invoke another property of typical sets, that everything inside a typical set roughly has the same probability. So under that question, that given a sample from the product distribution, what is the probability that you mistake it as coming from the joint distribution? that is very almost precisely number of guys in the typical set for the joint distribution divided by total number of guys in the product distribution, which is roughly 2 to the n hxy divided by 2 to the nhx plus hy, which essentially gives you this quantity.
So this is basically what you're saying. So size of the typical set for the joint distribution is roughly this. Okay.
Yeah, that's
which we saw last time, and we also know again we remarked for the noiseless coding theorem that all the typical sequences have almost uniform probability. I mean, there's a fudge factor, but it's essentially uniformly distributed over this set. So the size of the typical set for x times y is just the product. Okay. Which in the exponent becomes a sum, so which looks like this. So now, because things are like uniformly spread out in a certain sense, so the probability that if I take a random sequence from here, okay, so this is the so choosing from the product distribution here means I'm taking a random element from here. So if I take a uniformly random element from this set, what is the probability that it lies in the smaller set? So you can see that you expect it to be the ratio, and the ratio of it is just the mutual information. Okay, out here. So let me also write that one.
So it's those fudge factors that feed into this delta, right?
Yeah. So that's why you get 1 plus minus. So there were fudge factors with probabilities of all typical sequences. So they. Yeah, that's basically what it is. And recall that this is the mutual information. Good. Yeah. Any further questions? Okay. So let's go ahead. So let us finish this analysis. So we are analyzing the expectation of the decoding error probability, and we upper bounded it by this expression, as you saw. So now if I take R to be less than this quantity, this shows that the expected error probability can be made less than 2 epsilon for large N, which means that there exists a code book so that the probability of error averaged over all messages is less than 2 epsilon, just instantiation. So this proves the achievability of N times the mutual information times the fudge of 1 minus delta as the rate for N independent users of C. And it turns out that the error probability can be kept small even for the worst case message by a small sacrifice in the rate. Okay, so this is what people who have seen the standard information theory code. This is what they call the expurgation of the code book. But in this course, we will not bother with the expurgation so much. So you can throw away those messages whose decoding error probability is too high. Okay, so you lose a little bit on the rate, but now you can ensure that the worst case error is less than 4 epsilon or something like that. Okay, but asymptotically, the rate still looks like N times the mutual information times the fudge of 1 minus delta. Okay. Any questions about that? So we have done the achievability. Any questions? Okay, so we will not look at the proof of the converse today, but instead in this course we'll do something better. Like as you can expect, we will analyze this with our one-shot tools, and we will get an achievability result. We will get a matching converse result, and I mean, if the last lecture anything to go by, our analysis will be far sharper than this fudge factors of 1 plus minus delta at the end of the day. Okay, so we want to shoot for a one-shot noisy channel coding theorem. So now the picture looks like this. So the message n is something from 1 to 2 to the r. Okay. And it goes to an encoder. So the encoder produces a code word which I'll call xm. So the code word is just a symbol from the input alphabet to the channel. The channel is applied exactly once, and then it produces a probability distribution with output alphabet. The decoder gets a sample from the probability distribution and comes up with a guess m hat for it. Okay, and of course we want that the probability of m hat not equal to m is less than fsl, where the probability is over the uniform choice of the message and the randomness introduced by the channel. And again, I mean, for achievability, we will look at encoder and decoder. It will turn out encoder and decoder can be kept deterministic. Our converse will also hold if the encoder and decoder use private points. Okay, so what we want for this setup is good lower and upper bounds on the achievable rate R. So for this, as we will see later on, we will need an appropriate one-shot version of mutual information. So it is called a smooth hypothesis testing mutual information. But before we do that, it will pay to study a little bit of traditional information theory, because it will give us a good idea of the entropic, the one-shot entropic quantities that we'll use later in the course. So let us revise the Shannon relative entropy, which is also known as the Kullback-Leibler divergence. And it is the mother quantity behind all these Shannon entropic quantities. Okay. So we'll do that. And then what we will do in the next lecture is that we'll generalize the Shannon relative entropy to smooth hypothesis testing relative entropy. And the hypothesis testing relative entropy will lead to the hypothesis testing mutual information. So this quantity will lead to this quantity in the same way as the Shannon relative entropy leads to Shannon mutual information. So I haven't told you how it leads, but you'll see it shortly in a few slides. Okay. So this is the plan for the rest of the lecture. Okay. So what is the relative entropy? So let us say I have two probability distributions P and Q on the same sample space X. So the relative entropy is defined by this quantity. So this is the notation, okay, and this is the expression. So it is the average of this random variable. So if I think of a random variable which maps the sample point X to this quantity, log of the ratio, okay, so it's called the log likelihood ratio in the technical term. Now, if I take the expectation of the log likelihood ratio random variable under the first probability distribution P, I get the relative entropy. So you can see it's an asymmetric definition because there is P here. Okay. So properties, which we'll prove shortly. So the first property is non-negativity. So the relative entropy is greater than or equal to 0 for any PQ. It is finite if and only if the support of P. So recall the support of P is the set of sample points with non-zero probability under Px. So if the support of P is contained within support of Q, then this quantity is finite, which you can easily see from this expression. Okay. And what may not be immediately clear is this quantity is 0 if and only if P is equal to Q. Note that this random variable can be both positive and negative, because there can be sample points X where Px is larger than Qx, but there will also be sample points X where Px is less than Qx. Okay, so this random variable, it can also be 0 if Px is equal to Q. So this random variable takes all real values. Okay, so it's not even clear a priori that the expectation of this random variable is a non-negative quantity. So the first non-trivial property is that it is indeed non-negative, and moreover it is 0 if and only if P is equal to Q. Okay, so there is a strict non-negativity. So that is why I can think of this as an asymmetric notion of distinguishability between probability distributions P and Q. Asymmetric, why we'll see shortly. Next property is the continuity. So relative entropy is continuous in the probability vectors P and Q when it is finite. Okay, so we know when it is finite. As long as it's finite, it's continuous, which is because of continuity of the log function. Okay, data processing inequality. So this is a very important inequality, and as the course proceeds, you will just see how important this property is. So what does it say? It says that if I take two probability distributions P and Q, but now I'm thinking of the probability distributions on a joint alphabet X, Y. So the relative entropy of the joint probability distribution is larger than the relative entropy of the margins. Okay, so this notation henceforth will denote the joint probability distribution on the alphabet x times y, and this is the marginal probability distribution I get on x. And as you can guess, a similar thing will also hold for the marginal y. So the joint probability distribution is always greater than or equal to, I mean, the relative entropy for the joint probability distribution is always greater than or equal to the relative probability, relative entropy for the marginals. And as you can see from the asymmetric definition, and you can verify by concrete examples, the relative entropy is not symmetric. In fact, even if I symmetrize it naively like this, it does not satisfy the triangular inequality. So the relative entropy does not form a metric, unfortunately. So let us say I symmetrize it. So it's symmetric. It is strictly positive because of this quantity, because of this property. So that's good, but unfortunately, even after this symmetrization, it does not satisfy triangular inequality. So it's not a metric. It also looks a little hairy because of the log function, but as you'll see, it's a very useful quantity. So that's why I'm calling it the mother entropy quantity. So any questions about the definition and the properties?
Data processing is true even for random maps acting on random f acting on x and
Yeah, I'm coming to that. So it is not clear why I'm calling this a data processing. Okay, but bear with me; it will become clear in the next few slides. Okay, but I'm just saying, is this statement clear? The relative entropy of the joint distributions is greater than relative entropy of the marginals. Okay. Yeah. Okay. So this is relative entropy. This is data processing. So a consequence of this data processing inequality is what Shannon just said. So let us say this calligraphic D is a private coin algorithm mapping input symbols from X to probability distributions over output symbols from Y. So I use calligraphic D to remind you of the decoding, the private coin decoding algorithm, but in general it could be any private coin randomized algorithm. Okay. So what is this algorithm D doing? It is acting on a sample from Px, okay, which is coming from the probability distribution Px, and it produces a probability distribution on Y. Similarly, if the algorithm is fed a sample from Qx, it produces a sample from Y, but with some other probability distributions. So I can talk of the relative entropy between these two probability distributions on Y. It turns out that this is less than the original relative entropy. So in other words, data processing, I mean processing by this algorithm D, cannot increase the distinguishability. Relative entropy was kind of an asymmetric measure of distinguishable probability distributions. So any processing of data can only reduce the distinguishability that was there to start off. So that's the message. Okay. So let's take a 5-minute break. I will pause the recording so you can open your books and try to prove this. Okay. So you can prove it directly using concavity of logarithm and all that, but I encourage you to try to prove it from this expression, okay? From this statement of data processing. Okay, let me pause the recording for now. Okay. Yeah. So yeah. So as Shunandan just said, think of the algorithm D as something that induces a joint distribution between the input X and output Y. Then the left-hand side is indeed the marginal on Y. But if I have to use the data processing as given here naively, then the right-hand side should have been PXY, QXY, but that is not what I want. I want PX, QX. Okay. So here's the answer. So the action of the algorithm D on a probability distribution Px can be modeled by a 3-step process. The first step is to attach an independent fixed probability distribution RC to Px. So C is basically the coin space. So it's a private coin algorithm. So RC models the private coin of the algorithm. Okay. So the private coin starts off in some probability distribution, which is completely independent of the input. Okay. So this probability distribution I'm calling RC. And attaching it just means that I'm going from the distribution P on X to the joint distribution on XC, but the joint distribution is a product distribution. It's a product distribution which is P on X and R on C. This is the first step of the private coin algorithm. After this, C becomes a deterministic function. Sorry, after this, D becomes a deterministic function. Okay. So why is that? Because now the coin has been set. So the deterministic function can be thought of as mapping the input X and a sample from the coin C to some function f of X. Remember this function f is supported on Y. Okay. So f maps X comma C to the alphabet Y. Now it turns out this function, it's an arbitrary function, can be made into a bijection, capital F, as follows. So now I enlarge the input space. So I think of X, C, and there is another register Y. Okay, this register is basically the output register. But now I'm also attaching to the input. Let us say for the algorithm, the output register is initialized in the all zeros state to start off with. Okay. Now the function capital F maps it to this quantity Y XOR f of X comma C. So this denotes the bitwise XOR. So remember, f of X comma C is supported on the alphabet Y, so it's a bit string, okay, of the same length as Y. So you can do the bitwise XOR. And now, so what is the second step? The first step was just attaching the private coin. The second step is to apply this bijection F to the probability distribution Px times Rc, and actually there should be 13 times the all zeros distribution on Y. Okay, so there should be a 0Y out here, which I'll correct it when I put up in the slides. Okay, so now after I apply capital F, the desired output that I want. Remember, at the input of capital F, what do I have? I have the input X, I have the private coin C, and I have all zeros for the output register. And now after F is done with, I'll get the function value in the output register, which is exactly what I want. So the third step is just to discard the registers X and C. So any private coin algorithm can be modeled by this three-step process. Okay. Is this clear to everybody?
What is that last step like?
Last step, discard.
Like,
Remember, the algorithm was supposed to send X to Y, right? So all these are internal things. So it first sends X to X comma C by putting in this probability distribution over the private coin, right? Then it also sends it to X comma C comma Y, where it puts the all zero strings on Y. Then it applies the bijection capital F. You can see that it's a bijection, right? If I apply, in fact, the inverse of F is F itself. If I apply F twice, I'll get back the original string X C1.
yes.
So I started with the register X, then I go, then internal the algorithm has registers X, C, Y. C is initialized to a sample from the private coin, Y is initialized to all zeros, then F is applied, and then I only want to keep Y, right? So I just discard X. So that's the last. So in terms of probability distributions, what does it mean? Discarding X. So after step 2 is done, I am thinking of a joint probability distribution on X, C, Y. Okay, as you just thought of, I'm thinking of a joint probability distribution X, C, Y, not on X, Y. And now to go to Y, I'll just discard the register X. So steps 1 and 2, you can easily verify, don't change the relative entropy. Okay, attaching this fixed probability distribution. Okay, remember, whether I start off with Px or Qx, I attach the same RC. So that does not change the relative entropy. Okay, attaching all zeros to Y out here also does not change the relative entropy. So steps, the attaching steps in 1 don't change the relative entropy. Then applying a bijection does not change the relative entropy. So come here. So if I apply a bijection on X, okay, it's just a permutation on X's, but the summation still remains the same. So step 2 also does not change the relative entropy. Step 3 is the only one that can decrease it. So that is this data processing inequality, discarding X3. Okay. So that finishes the proof. So I started off with Px and Qx. Then I went through steps 1 and 2. So I got Pxcy, Qxcy. Relative entropy still remains the same. And then I discard Xc, okay, to get Py and Q out here. So that can decrease. So the moral is relative entropy is an asymmetric measure of distinguishability between two probability distributions, and data processing cannot increase the original distinguishability. Okay, and this consequence justifies the name data processing. Okay, really, I mean, these for data processing. So this is clear to everybody. Okay, so in information theory, in the course of proofs, you'll have encoding algorithms, decoding algorithms. You'll come to relative entropies before and after encoding, decoding. So remember that whatever you do, okay, as long as it's a private coin procedure, it is nothing but data processing, and you can apply this inequality. So it can be applied in very powerful ways. Okay, but it all boils down to this quantity. Okay, so here is another property of relative entropy. Often people state it as a different property, but I've chosen not to do it, just to illustrate that even this property follows from the data processing inequality output. So this is just to give an idea how powerful data processing is. So this property is what is called joint convexity of relative entropy. So let us say I have these 4 probability distributions, P0 and P1, okay, and Q0 and Q1, they're distributions on X, and P is some number between 0 and 1. Then I can think of this probability distribution. So this is a convex. So the probability vector is a convex combination of probability vectors P1 and P0. So convex combination means the coefficients are positive and add up to 1. So P plus 1 minus P equal to 1. So I take the same convex combination of Q1 and Q0. And convexity, the joint convexity means that whatever convex combination I take here, for P's, I take the same convex combination for Q's. So that is upper bounded by this expression. Okay, the convex combination of the individual relative entropies. So how to prove it from data processing? So take the alphabet X and attach a fresh bit B to the alphabet. Okay, so I'm enlarging the alphabet. And now consider the joint probability distribution on XB, defined as follows. So probability of X comma 0 is 1 minus P times the P0 probability distribution. Probability of X comma 1 is P times the P1 probability distribution. And similarly for QXB. Okay. So I define it like this. Then you can see that the left-hand side here, okay, is nothing but the relative entropy of the marginal probability distribution. So I have this joint probability distribution P on XB. I can take the marginal on X. Okay. Similarly, I have the joint probability distribution QXB. I can take the marginal on X. So I can talk of the relative entropy of the marginals. And the probability vectors will be precisely these two quantities. So this is the left-hand side. And the right-hand side, again, you can check with a little bit of calculation, is nothing but the relative entropy of the P on XB with respect to Q on XB. Okay. So just the simple data processing I can apply and calculate this. So what is the moral? The data processing implies joint convexity for Shannon relative entropy. Questions about this proof? Okay. So let us prove this amazing data processing inequality. So this data processing inequality follows from what is called the chain rule of relative entropy. Okay. So, I mean, again, you can prove it directly, but I've chosen this proof because it gives you another nice property that you need to know, which is the chain rule. So chain rule is this. On the left-hand side, I have the relative entropy between the joint distributions on XY, P and Q. So a chain rule is something which breaks the entropic quantities on joint distribution into some sums of entropic quantities on the marginals. So the entropy on the joint distribution is the entropy on the marginal next plus some quantity. So what is this quantity? So let us fix capital X to some instance, to some symbol little x. So this induces a conditional distribution on y. So that's what this notation means. Py given x equal to little x means fix the first coordinate to little x, and now look at the conditional distribution on the symbols y. You can do this for p, you can do this for q. You can look at the relative entropy between them, okay, and then you can take the expectation of this quantity as the little x is chosen according to the marginal norm px. Okay, so this is the second term, and the sum of these two happens to be this. It's easy to prove just from the definition. So the left hand side is this quantity. Okay, so normally I would have written it as px comma y log px comma y divided by qx comma y, but I'm writing px comma y as this product expression, marginal on x times the conditional. Okay, similar like this. So now I can just break it up into something like this. Okay, and now look at the second summation out here. So this is precisely the second term out here. So this is the right answer. Everybody follows this proof? Okay. So I have proved the chain rule, but how to get the data processing? All I have to show is that this relative entropy is greater than or equal to 0. So remember, we had this property, right? The very first property, non-negativity. So basically, I'll sit and prove the non-negativity property of relative entropy. So we'll show that for any two probability distributions A and B on the alphabet Y, the relative entropy is greater than or equal to 0. And for this, we'll appeal to the concavity of logarithm. So this is a log function, and concavity just means that I take 2 points on the curve and take the chord between them. The chord lies below the curve. So this is what concavity means. So in other words, if I take a point on the chord in somewhere in the middle, it lies below the curve. In other words, the expectation of the logarithm. So let us say I take the 2 endpoints. Okay. So expectation of the logarithm is the point somewhere in the middle. Let us say I take the first point with probability 1 minus p, the second point with probability p. So and let us say p is small. So the point lies somewhere close to the left. So now the expectation of logarithms is this point on the chord. That is less than the log of the expectation. So log of the expectation is the point above on the curve. Okay. So concavity means that the chord lies below the curve, or in other words, the expectation of function values is less than function value of the expectation. So let's use it out here. So this relative entropy, I can write it like this. Now I've used the negative sign because I have taken reciprocal here. And then I apply the concavity, and because of the negative sign, I get greater than or equal to. So it is this is the expectation of logs. Remember, AY is a probability distribution, so this is the expectation of logs. That is less than the log of the expectations. So I have this log of the expectations, so which turns out to be this one. Remember, BY is a probability, so this sums up to 1. So this completes the proof of the non-negative relative entropy, which completes the proof of this data processing inequality, and also tells us something more. It gives us the condition for equality in the data processing inequality. So what is the condition for equality? So every term here has to be 0. In other words, for every little x, the conditionals on y should be the same. Right? This is what this is saying. And where did the equality come from? Remember, the logarithm is strictly concave. So in other words, take the chord, every intermediate point on the chord lies strictly below the curve. Okay. So the only way you can get equality out here, okay, is if one of the AIs is 1 and the others are 0. Okay, so that's the strict concavity out here. So if but if you do that, I mean, if I take one of the AIs is 1, the others are 0, then the relative entropy also becomes trivial. Okay. So the other way out is that all the function values are the same, all the logs are the same, which means that AY is equal to B1. So the strict concavity logarithm implies that equality is implies that relative entropy is 0 if and only if AY equal to BY, okay, which translates to this expression. Any questions? No? Okay. Yeah. So why did I call the relative entropy as the mother entropic quantity? So the mutual information, which is normally defined this way, can be written in terms of relative entropy. So remember, for the mutual information, I had this joint probability distribution P on XY, okay, P on XY out here. So it is nothing but the relative entropy of the joint probability distribution with respect to the product of the margins, the independent product of the margins. The conditional probability distribution, which is defined like this, okay, the conditional entropy, which is defined like this, entropy of X given Y, which is defined by the expression on the left, turns out to have this expression, the relative entropy. So, so take the joint probability distribution Pxy and look at the relative entropy with respect to this product of probability distribution. So it's the marginal on Py times the uniform on X. So if you do this, and then there's a little bit of logarithm and subtraction, you'll get this quantity. Again, easy to check. Okay. And once I have got the conditional entropy, the good old entropy, the unconditional entropy is very simple. It is nothing but the conditional entropy when the alphabet Y has size 1. So in that sense, even this entropy can be related to the relative entropy out. So this is indeed the mother quantity. And many properties of entropy, conditional entropy, mutual information, etc., follow from properties of relative entropy. So you may have read about concavity of entropy. Then there are convexities of mutual information. Then there are data processing inequalities for conditional entropy, data processing inequalities for mutual information. Lots of things here and there. Additivity of entropy, subadditivity of entropy. All of these can be proved from properties of relative entropy. And what properties? Just the properties that I've told you. Strict positivity of relative entropy, okay, and data process. That's it. That's all you really need to know. Any questions? Okay, so I think we'll stop here, and we will stop at this point. And yeah, so I invite any concluding questions, doubts. Okay, if not, then I'll stop recording and I'll see you on Tuesday.